Before knowing the evidence of dark matter, let's first understand what dark matter actually is. First of all, we must understand what is dark matter. It is believed that this mysterious type of matter that no one can see makes 27% of the content of the universe, while visible matter, you, me, all stars and galaxies, counts for only 5%. Evidences of dark matter. 1. Galactic rotation curves. The most direct evidence of dark matter's existence comes from measured rotation curves in galaxies. According to the Newtonian formula for velocity v of a body with mass m orbiting a galaxy at a distance r from its center, the velocity v is inversely proportional to the square root of the distance r. So as expected, the velocity of the orbiting body should drop off with an increasing distance from the center. The surprising discovery was that as the distance from the center of the galaxy increased, the velocity of the orbiting body was observed to stay at a constant peak value. This indicates that the orbiting body is gravitationally pulled by some another of matter other than the luminous matter. Hence, it constitutes direct evidence for dark matter. Many subsequent studies confirm this discovery. 2. Bullet cluster and gravitational lensing offers direct empirical evidence of dark matter. This is the observational result shown above. Bullet cluster are displayed above. The picture on galaxies that make up a few percent of the cluster mass. Superimposed on top of these two pictures are the mass contours as derived from gravitational lensing. These contours have two mass peaks which, while they more or less track the locations of observed galaxies, are situated at very different positions from the atomic gas. It is consistent with the interpretation that this bullet cluster came about because of a collision of two clusters of galaxies. Dark matter and baryonic gas are separated because the dark matter, having small interaction cross-section, passes through like a bullet, while baryonic gases are left behind. 3. Dark matter evidence from the CMB, cosmic microwave background. On a larger scale, the abundance of dark matter can be quantified from the study of large cosmic structure and CMB. All this leads to a total mass density equals 0.25, of which the total baryonic density is 0.04 and the total dark matter density is 0.21. So the luminous matter associated with the stars we see in galaxies represents about 2% of the total mass content. Evidence of dark energy. The evidence of dark energy was found out by studying special supernovae, called standard candles in cosmology. These are type Ia supernova, discovery of an accelerating universe. Because light from distant galaxies was emitted long ago to measure a star, or a supernova, farther out in distance, is to probe the cosmos further back in time. An accelerating expansion of the universe means that the expansion rate of the universe was smaller in the past. In 1998, two collaborations, the Supernovae Cosmological Project and the High-Z Supernova Search Team, studied some 50 SNE-Ia at high redshifts, corresponding to SNE occurring 5 to 8 billion years ago. They made the astonishing discovery that the expansion of the universe was actually accelerating, as indicated by the fact that the measured luminosities of the supernova were on average 25% less than anticipated, and the Hubble curve bent upward. Hubble curve is a plot of the luminosity distance versus the redshift, measuring recession velocity. Below is the graph showing the Hubble curve, plotted dots on the graph. We can see that the curve is bent up.